Hello, everyone. I'm Jeannie Linky Northrup, Managing Editor with Turbo Machinery International, and I'd like to welcome you all to today's live broadcast, Sealing the Future, Using Innovation to Accelerate Carbon Capture, Utilization, and Storage, sponsored by John Crane. John Crane is a global leader in mission-critical technologies for the energy and process industries and an innovator in rotating equipment encompassing mechanical seals, couplings, filtration systems, cutting-edge asset management, and digital diagnostics solutions. Blending a rich legacy of innovation with a commitment to serve excellence, John Crane has enabled its customers reliable and sustainable operations for more than a century. Before we begin with today's webcast, I have just a few important announcements to make. First and foremost, this webcast is designed to be interactive, and so we encourage you to ask any questions you have for our presenters throughout the event. You can submit your questions by typing them in the Q&A box. That can be found at the bottom of your video player. You can also enlarge the slide window by clicking on the small icon in the bottom right corner of the media player. Please note, however, that all slides will advance automatically throughout the event. If you do happen to experience any technical problems viewing or hearing the presentation, please click on the question mark help widget in the top right of your presentation window. So in today's webcast, we are joined by John Crane's very own Volker Hins and Humberto Castillo. Volker and Humberto will review the fundamentals of dry gas seal technology, and they'll share their insights pertaining to properties of CO2 and particularly the utilization of sealing technology. That said, I'd like to now welcome and further introduce both Volker and Humberto. Volker, a global product manager for John Crane, has been with the company since 1990. He has a background in mechanical engineering and more than 3 decades experience working particularly with dry gas seals. Humberto is a staff engineer with John Crane's UK dry gas engineering team. His background in mechanical engineering has allowed him to support a diverse range of projects, although he specializes in energy transition areas like today's topic. So that said, gentlemen, thank you so much for your time today. Feel free to begin your presentation.
Hello and welcome to the webcast with the topic Sealing the Future, Using Innovation to Accelerate CCUS. First of all, I'll go through the agenda, which we will start with a short introduction. The dry gas seal basics, physical properties of CO2, following by sealing solutions, topics, supercritical CO2, a short market view about the future CCUS projects and market size, and finalized by Q&A. Introduction. John Crane is part of the Smith Group, and in this conjunction, the biggest company of the Smith Group is the largest business. Smith Group itself is a global technology company listed to the FTSE 100 index. Smith Detection, Smith Interconnect, and Flex Tech, and we serve the following markets worldwide, which is energy, security and defense, general industry, and space and aerospace. John Crane itself is located all over the world. We have more than 200 sites in more than 50 countries. We have 163 sales and service centers, including in these 163 sales and service centers, we have 12 so-called dry gas seal service centers, which are located as well around the globe. We have 35 manufacturing sites with more than 450 CNC machine tools around the world, and 9 engineering and R&D global hubs. And in these service centers and manufacturing sites, we have 115 test rigs. A certain amount of them are supposed to run dry gas seals. A short overview over the products and services. We are aside the sealing and sealing systems. We have a portion of filtration. We are manufacturing the systems supporting the seals, either mechanical seals, wet seals, or dry gas seals. And as well, we have a certain amount of couplings which we can deliver to the field. Besides that, we are focusing on servicing or services our customers, which is support in project design and management, aftermarket repairs and services, methane abatement solutions, turbo machinery upgrades, reliability and inventory programs, and asset management solutions. And finally, we provide training worldwide for all kind of products we deliver. Going now to the dry gas seal basics, I'm pretty sure that a lot of the audience know about dry gas seals. However, for listeners, participants which are new to the product, a short review. This slide is showing the main components of a dry gas seal, which is starting with the dark gray one. Is the rotating parts, the shaft sleeve. Then we have on the bottom right side the centering devices, which fixes the rotating seat or mating ring, which is the red part here. Then we have the stationary parts, which are the retainer, the internal labyrinth, and the stationary face or the primary ring, and to seal it internally or against the carrying parts, we have the secondary sealing elements. In this image here, polymer rings. So we have the seal itself on the right hand side. On the left hand side, you see a barrier seal which prevent oil migration coming into the seal area. And the arrangement here is showing a tandem seal, which is approximately 90% of the seals in the field are this kind of arrangement. The function of the seal, as mentioned, on the left-hand side you have the separation seal. On the right-hand side, the seal itself. Right is the process area, left is the bearing area. So you will serve the seal with filtered process gas in the front of the seal to avoid any contamination of the inboard seal, which is on the right-hand side. A small portion of these filtered process gas will go through the inboard seal. This leakage will then go to primary vent. The third port from the right-hand side is the nitrogen buffer purge. So here in green, you will see, or the arrow in green, nitrogen will be flushed into the seal. This bigger portion goes underneath an internal labyrinth and will be vented together with the inboard leakage to primary vent. Safe area will be flared, whatever is possible at site. On this outboard seal, the second sealing stage from the right-hand side, a certain amount of nitrogen will leak to the secondary vent, and the bearing area separated by separation gas will be, let's say, supported by these nitrogen barrier gas or an air, and a portion of that will be leaked to the bearing, another portion will be leaked to the secondary vent and go together with the nitrogen buffer purge to the secondary vent, normally to atmosphere. The next slide will show you the principle of the dry gas seal. So in the primary ring, in the rotating seat, we have placed some grooves. This image here is showing the patented single grooves from John Crane. The blue ring, the primary ring, is spring loaded, means it's flexible, and when the seal starts moving, the gas will be routed into these grooves. At the end of the grooves, there will be a pressure peak, and this pressure peak will allow the blue stationary phase to separate from the mating ring, and the seal will run on a gas film. So as soon as the lift off speed is reached, the seal will run contactless, without contact. And this animation here will give you a short the function. So on the right hand side is the process gas, then the blue one is the nitrogen serving to the gas, and when the seal starts moving, you will see that this seat, respectively phase, will be separated, and the seal, as mentioned, is running then contactless. With this short introduction, I'm passing over to my colleague Humberto. Thanks for listening.
Brilliant. Thanks, Volker. I'll continue the slides, and the next topic to talk about is now physical properties of CO2. And we thought it would be prudent to start talking about air. So CO2 is obviously well known to us, but how does it relate to the air we breathe? So just as a breakdown of composition, we can see CO2 forms a very small part of the air we breathe, around 0.04%. But what we wanted to share with yourselves is this graph from an observatory in Hawaii, where they've tracked the increment over time of CO2 in parts per million. And they started recording this data from late 50s, I think 59, and we can see there's been an increase of almost 47%. So basically, we're going from 280 parts per million to 412 parts per million as of today, showing the impact of human activities, particularly the effects of burning fossil fuels, and how now the topic of CCUS becomes more and more relevant. The next slide, we will talk about physical properties, but now looking at a phase diagram. So just to share with yourselves, as all fluids, we have three distinct phases. So we have gas, liquid, solid. But CO2 is a bit special as it has an extra phase, which is supercritical. We call it supercritical or dense phase, where there is no distinct definition between a liquid phase or gas. And the points to mention are the critical points. So in the middle of the partition between liquid, gas, and supercritical fluid, this happens approximately around 74 bar and 31 degrees C. We also have a triple point, which is where we have the convergence of solid, liquid, and gas. and that is roughly around 5 bar at minus 57 degrees C. On the right-hand side of the screen, there's a table as well, where we wanted to mainly give the audience an order of magnitude when we compare different fluids in their different phases. So when we look at gases, from a density perspective, they're very low. From a liquid perspective, they're obviously relatively higher. And supercritical sits in the middle. So we can say from a density perspective, supercritical actually is more akin to a liquid than a gas. But then when we look at viscosity, it actually reverses. So we see that actually supercritical fluids are more related to a gas than a liquid. And this dichotomy, this duality in behavior is what makes CO2 and its supercritical phase so relevant. And over time, I can say there's been many attempts to model the behavior of CO2 from its physical properties perspective, from basic equations of state from van der Waals to Ping-Robinson in the 70s, and then later on with Span and Wagner, where there's been an attempt to understand what's happening within that transition area, so where we move from liquid to supercritical or from supercritical to gas. The last point to mention on this graph is we had this dotted line reflecting that break point between the different phases, but they're only theoretical as those sudden transitions do not exist. There's many aspects that will affect when and how the change in phase occurs. Then to share another part of the presentation is to talk about density. So density of CO2 is quite interesting how it behaves. And what we can say is that supercritical CO2 specifically has a high density, but it maintains some compressibility, which it makes it quite unique, particularly for dry gas seal applications. And one of the important points is to note that whenever we operate near the critical point, this can actually cause large variations in density with only minor changes of temperature or pressure. This is depicted in this graph where we're seeing these lines, which are quite hectic. They're changing as we go down the screen. They're increasing in temperature, where we have on the vertical axis density, and on the bottom we have pressure. So we see how as we increase in pressure, density starts reducing, and there is some sort of there still is some compressibility as those slopes are gradual, but not obviously as much as what we expect in a liquid. And the graph on the right hand side is now depicting a comparison between an inert gas like nitrogen, which is prevalent in dry gas seal applications, as Volker mentioned in the previous slides. And this is specifically at 67 degrees C, and we can see how this changes with pressure. So there's a large discrepancy between CO2 and N2 when we look at density over pressure. Then the next property, which is quite important as well, is viscosity. And what we can say is supercritical CO2 has a high dynamic viscosity. But then when we look at the graph here, when we take into consideration density, then we're obviously understanding how CO2 behaves in relation to kinematic viscosity over pressure. And we can see how different it is in relation to, again, an inert gas like nitrogen at 67 degrees C, and how this changes with pressure. So also, as we mentioned with density, the same situation occurs with viscosity, where when we operate near that critical point, we would expect large variations in viscosity with only minor changes in temperature or pressure. Because of this low kinematic viscosity, this actually translates into a larger leakage. So we would see, comparatively speaking, when we look at nitrogen, if we're looking at the same sealing gap, we would expect to leak more with CO2 compared to nitrogen. And that's quite crucial when we're trying to manage the performance of the seal. Also, another element to point out is during high-speed applications, this can also pose challenges due to viscous heating, which is well known within industry. Moving on now to churning losses. This is something that a lot of times is sort of not considered. It's challenging first to predict the behavior, and it's something that John Crane has spent, I would say, significant amount of time and resource into trying to define and create a more robust model specifically for dry gas seal applications. So if we take a step back, what are churning losses? In essence, these are specific in a way maybe to high viscosity fluids like supercritical CO2, where there's a lot of heat generated in the seal. And it's mainly due to the components which are rotating, obviously at speed, and these cylindrical components, they have very tight clearances, which is in a way the images that Volker showed in that tandem arrangement. And those tight clearances and that heat which is being generated is what we call churning loss. In essence, it's a power loss, and the approach that John Crane took was to look at literature, and there were different models, but they approached it for, I guess, a generic cylinder or disc, where we have had two engineers with from John Crane, Klaus Meck, and a colleague surnamed Ju, where basically they've improved on the predictions via a coefficient, a flow coefficient, which appears in this equation in the middle, referred to torque. That C sub F coefficient is what's been modeled in a more robust and more predictable way for dry gas seal applications, and it's allowed us to understand more about the heat balance of the system within the dry gas seal, and also try to predict more about the expected temperature differential. And to finish off about churning losses, we can just graphically represent with this churning losses to speed graph, and we can see that as we ramp up in speed, these churning losses become significant and they need to be considered. Then moving on, we will talk now about sealing solutions. So John Crane has many products, but within dry gas seal and tool machinery products, we can seal CO2, particularly when it's around this critical point, with the product 28VL. So this is mainly deployed in pumps, and the idea behind it is that it's basically it harnesses the energy which is imparted by the rotating machine to vaporize a process fluid. So in essence, we are with the heat generating, we're flashing the fluid and changing the phase from liquid to gas. This allows us to deploy our non-contacting dry gas seal technology, patented in the 70s, to basically enable the performance of the seal. This image is a cross-sectional view of the VL, and what we can say is that this has been proven in the field. There's robust performance with hundreds of seals operating successfully in the field. Then moving on, we have the dry gas seal when CO2 it's in its gaseous phase and also supercritical phase. We can deploy these other products, which are the 28AT, XP, or EXP, and that will depend obviously on the pressure capability of the seal and obviously the application. And here, this is more akin to compressors because it's prevalent in high-speed applications or higher speed, so in the order of tens of thousands of RPM. Again, proven design technology based on the T28 non-contacting dry gas seal technology. And again, we can say robust performance, hundreds, if not thousands of seals operating successfully in the field. This cross-section is of a EXP, which is similar to the image that Volker shared before, with the exception of, because of the high pressures at EXP, have to endure. We have this ADC balanced diameter polymer in the middle of the screen, the big black element, which enables the prevention of a polymer jacket extrusion. Then moving on to talk about supercritical CO2, specifically, we can refer to its complexities. So we've mentioned about the critical points being at 74 at 31 degrees C. We've got this high density and viscosity, but maintain some compressibility element, which is referred to. And obviously, we've mentioned about what happens when we operate around the critical point and how we would expect big changes with relatively small changes of temperature and pressure applying for both density and viscosity. But one element which is particularly interesting is something that might sound counterintuitive, which is actually when we increase gas injection temperature, this can actually reduce the heat generated. And logically, one would expect the opposite. So if we increase the injection temperature of the seal, then the heat would increase. But what we need to remember is when we're dealing with supercritical CO2, as we move to the right-hand side of this phase diagram, so increasing in temperature, density starts reducing. And because of that, it takes less effort. Therefore, there's less heat generated in losses to basically rotate that mass of fluid within the dry gas seal. Also, another element is that when holding high pressure statically, this can also lead to icing on the sealing interface. And this is mainly explained by another phenomenon, which is that supercritical CO2 and CO2 itself has a large Joule-Thomson coefficient. And we understand this Joule-Thomson coefficient to be, in essence, when a fluid suddenly sees rapid expansion. So that causes a drop in temperature or reduction in temperature. So there's a cooling effect. And because we're holding this high pressure statically, we're in the supercritical fluid, as the dry gas seal will invariably leak over time, there is potential for any water vapor, so impurities within the CO2, to potentially move on to the liquid phase or potentially solid, which is why sometimes we've experienced some icing on the superface, on the interface. Moving on, so where are these supercritical CO2 applications found? Where do we usually see them? What in our experience we've seen from customers is we're mainly deployed in fertilizer plants, and there are new power cycles like the Alum cycle, which now is harnessing this duality of performance on supercritical, and they're trying to, in a way, create I guess a low carbon emission power cycle by utilizing the duality of how CO2 behaves. And obviously, regarding carbon dioxide capture, utilization and storage, which is where the topic of CCUS comes from. Then moving on, we have a case study, which is quite interesting to share with yourselves. This is a fertilizer plant in the east of Europe, where in essence, there was collaboration required between the end user, compressor OEM, and ourselves as dry gas seal suppliers, where the end user wanted to expand on their capacity of production on this fertilizer plant, specifically the production of urea, and they had also some antiquated recip compressors. So they wanted to modernize their equipment, and then on top of that, obviously increase their production. So this collaboration took place where John Crane provided a dry gas seal. There was a test loop that was commissioned at the compressor OEM facility to perfect the groove design and to ensure that when the compressor and dry gas seal were deployed in the field, the customer would be happy with the results. So the resulting element to this is that their integrally geared machine of 8 stages met all and exceeded the expectations from the customer in relation to mean time between failure and obviously achieving the production increase that they wanted. So there are other case studies focusing on CCUS specifically, but I think it was important to share that John Crane has experience in this field, specifically sealing supercritical CO2 itself. Moving on, I will hand it over back to Volker so we can continue with the next slides.
Okay, thanks, Umberto. Just one further note to this case studies. If you're interested in to get it more in detail or to see other case studies, go to our John Crane homepage, and we have them placed there, ready for download. So feel free to do it on your own. Following CCUS, why CCUS? Sure, all of us know that carbon dioxide is one of the most potent gases in the air beside methane and responsible for the climate change. So the target of zero emission will mean we have to take care about the CO2 in the air, and there are several scenarios to reach the net zero target, which is expecting in 2030 that 1,000 megatons of CO2 has to be captured by then. And I don't want to go through these graphs in details. We have used several sources here, but the next slides is showing the increase of projects in this field. And you see in 2020, 65 projects were announced. In April 2021, 101. In January 22, 137 located around the world. And there is a statistic from fall of last year where over 600 projects are already announced and scheduled over the next years. And these projects will comprise several ways of capturing CO2 and store it at the end of the day or use it for other applications. And there are several different technologies currently available or in development, and with a wide range of providers. Here is just a sample of that. And as mentioned already, this will be a focused industry in future, and all of these technologies more or less need sealing solutions. This is the last slide from us, which brings us to the Q&A session. Many thanks for your attendance, and I'm opening the floor for the Q&As. Thank you very much.
Gentlemen, thank you so much. Great presentation, very educational, and it's also great to see what else you guys are working on in the industry to help improve these conditions. That said, we are getting ready to jump into our Q&A. I've seen some really great questions coming in from the audience. In fact, quite a few. So I just want to advise our audience that if we start to run low on time, don't be discouraged. Both Umberto and Volker will also review and can respond to your questions offline as well. Before we do get started, for anyone who may have signed in a little bit late, I want to remind our audience how you can submit a question to our presenters. You can type a question that you have in the Q&A box. That can be found directly below your video player. Okay, so let's kick off the session. Umberto, the first question I think would be great for you to help kick off. what would be the major differences in seals and, in fact, the sealing system designed for subcritical COT compressor applications and the compressors themselves?
Thanks, Jean, for that question. Thanks to the audience as well. So, from a design perspective, when dealing with subcritical, so gaseous CO2, the design would look very similar to one. I guess what the operator would see is very similar. There's no major differences in design. It's mainly how we attack the problem from the mating ring design and groove perspective. So from a CO2 perspective in gaseous phase, it would be our products XP mainly, and then as we jump into supercritical, which is mainly higher pressures, we could then be into the realms of our EXPs.
Great, thank you. Volker, was there anything you wanted to add to Umberto's points here based on your experience?
No, but it brings us to other question about the temperature and about this case study of the fertilizer plant. Though we are faced in all these supercritical CO2 applications with at least high temperature, and you have seen that these critical points, the supercritical point, is in brackets normal operation area. So it makes the CO2 sealing so special that we are talking about a pressure temperature range which is quite normal for, let's say, other gases as well. Anyway, it is addressed, especially the high temperature request with these new power cycles, and it's challenging. It's really challenging. Currently, we have some tweaks to get the temperature down, but the let's say the gaskets, the external sealing is a challenge here. Not really the sealing technology itself in terms of the gas seal technology, that we have a groove design and we have a lift off. We are talking here more about the secondary sealing elements, and it is challenging, really. We cannot deny that, but and it's a certain way to go, to be honest. There are the ideas flying around, but it's really too early to give a clear direction how to proceed in this regard.
Thank you, Volker, and I'm so glad you brought up the case of the fertilizer plant example, because I actually saw a couple of questions come in specific to thermal management and the DGS model for supercritical CO2. And I was wondering if you can kind of expand a bit more on the case, what was learned, and what the DGS model was in fact used for.
So in that case study for this fertilizer plant, it was an XP actually, so T28 XP. The realm of the phase was specifically supercritical. It was a integrally geared machine. I believe it was 6 stages. We were sealing the last 2 or 3 stages, and it was just basically an example of collaboration between end user, compressor OEM, and ourselves, working in tandem to provide a robust solution to the customer.
Great, thank you so much. So how do you prevent dry ice formation when the pressure is dropping across the seal phases?
I can take that one. In essence, the leakage when we're dealing with CO2 is very important. So the control of leakage within that interface between the primary ring and mating ring is what will cause this exacerbated Joule-Thomson cooling effect, which will then gradually shift the application point towards the left of that phase diagram. So we have 2 ways to combat that. So management of your leakage, so design of the grooves and the actual core of the seal, which is the primary ring and mating ring, to ensure that we minimize leakage, and or what John Cranes usually suggest in instances where this is not possible is the addition of a heater to ensure that we obviously condition the gas to always stay in that gaseous supercritical phase.
Thank you so much. Now, in the beginning of the presentation, you were able to highlight the widespread capabilities of John Crane across the globe. For the supply of CO2 application seals, are they available from all of your different factories, or are there select few? Which ones particularly in the North American market? Specifically looking to understand a little bit more from procurement, lead time, and the sparing philosophy. So kind of a loaded question, but where are the products available? And then what are the expectations in receiving the products and support?
I take this. Though we have 3 centers of excellences, and which are in Japan, in UK, and in North America, it's close to Chicago, and that all of them are able to manufacture seals for CO2 applications. So in principle, these seals, the seal technology, do not differ from our other dry gas seals. There are no specific parts which differentiate from other dry gas seals, and for that reason, we are not restricted in terms of the manufacturing capability all over the globe or in our service centers. And this brings us to the not service centers, sorry, to the manufacturing sites. But this brings us to the other point. It will as well not differ from in the perspective from lead times and procurement sparing philosophy from others. So if you want to purchase a seal for a nitrogen application, a hydrogen application, or a natural gas application, it's the same. There is no differentiator there.
Thank you so much, Volker. Great insight there. Our next question, a little bit more educational. Umberto, I'm going to throw this one over to you. Are elastomers used for secondary seals with the CO2 applications? And if so, what are the concerns about mitigating failure due to decompression?
Okay, so for CO2 specifically, we would always deploy an XP type seal, where our secondary sealing solution would be a polymer. This would, so it's basically an energized polymer, and this would not undergo any risk of explosive decompression. So that problem would be eliminated.
Awesome, really good to hear. And Volker, this next question I think would be more suited for you. What purity levels are normally assessed for CO2? What are you seeing?
The purity levels as well has the same like other gases as well, and this is in conjunction with the question of filtered process gas. Though we always recommend to have a pure gas in front of the seal to avoid any contamination, whether it's in liquid form or droplets, vapor, or gaseous in terms of particles. So we recommend purity smaller than 3 microns. So if you imagine that the gap of the dry gas seal, the gas film, is approximately 4 microns, which is a 0.20 of a hair thickness at the end of the day. So you can imagine it's very, very small. So the particles we want to have in front of the seal should be smaller than the gap. To avoid scratches and other issues. So the purity level should be that. And as mentioned, we always recommend a filtered gas or conditioned gas in front of the seal. And another topic which Umberto raised is probably a heater in front of the seal to change the density of the CO2 and to limit the leakage of the seal. So it's another thing we need to consider if it comes to a real project. So really, CO2 sealing is not a challenge, but it's a point of discussion. So we have to look into the projects, what's needed and what's needed. And as well with these, the question was about a backup source to feed the primary sea gas. Not necessarily. It can be from the discharge of the compressor, but as well we have to look into the complete environment of these specific project to give an advice. So it's not easy to state this in a, let's say, a global approach and say yes or no. It's a bit more than that.
Thank you so much.
Okay.
So what's the maximum decompression rate the seal can withstand?
I can answer that, Gina. I think that's quite specific. As an order of magnitude, we can say it's roughly around 100 bar per minute.
Great. Thank you so much. That's fast, real fast.
Yeah.
So when dealing with the pump, not the compressor, and you're going to go from pumping 130 to 190 right there, what is the suggested seal type? Now, I know we started to kind of go into that a little bit, talking about what your recommendations were. And I wanted to hear a little bit more, probably Volker, on your recommendations for what you would suggest in this scenario. And I know we were talking a little bit about tandem DGS types, which have been recommended for like more complex situations, but they seem a little complex to utilize, right?
Yeah, and you trapped me because I'm not the matter of expert of these Type 28 VL, so probably Humberto has a bit more idea
Sure.
of the
All right,
answer
well,
for
let's
this
roll it
question.
over to
Sorry about that.
Humberto there and throw you on the spot.
So in essence, the question is related to pumps. So
Yeah.
we would deploy the VLs for these lower speed applications, which are pumps. So I'm not quite what type of seal. I would assume it'd be a tandem. I'm not specific with the nomenclatures that we use internally through our extensive product range and pumps. But from the metering and primering perspective, they wouldn't be that dissimilar from what we deploy on our dry gas seals. So I'm sorry I can't be more specific in terms of what type of seal. Maybe we can answer that offline. Get back to the person that asked that question. Huh?
Yeah, absolutely. And what I was going to suggest is maybe our audience member can allude to a little bit more and introduce that question and request for that to be responded to offline. Thank
Sure.
you so much. Next question for CO2 applications on the compressors. What is the current market split of end user selections? What are you guys seeing for carbon ring seals or for dry gas seals?
I take this.
Okay.
That's a very good question, and it's currently a little bit changing. Though one of the points Umberto pointed out right at the beginning of his part of the presentation was that CO2 is a part of our air. So in the past, the end users did not really look at the amount of leakage. They were more looking about the technology to seal the compressor itself. So there was a split at around 40 bar where they changed from carbon ring design to a dry gas seal design. It was because of technology and because of the carbon ring amount of carbon rings they have to use in a cartridge. So this was, until now, I would say, the reason for use or where the split was between carbon rings and dry gas sealing. Because of the, or if we handle now CO2 as a product itself, which we want to keep inside, when we want to store it, we want to store as much as possible and don't want to let it disappear into the environment. So for that reason, this borderline from the technology side is changing now a bit more, because you have to consider that carbon rings leak much more than a dry gas seal, and for that reason we are faced more and more with the questions to seal CO2 even at lower pressures with a dry gas seal to keep the leakage as limited as possible. Another answer or another topic in this conjunction is seal design. We have spoken about a tandem seal at the beginning, because the tandem seal has the capability to seal more or to leak less than a single seal. However, sometimes it's really a decision from the compressor OEM, especially from the integrated geared machine OEMs, that they decide to go with a single seal, which will have the same sealing capabilities in the inboard stage of a tandem seal, but they have to look at other topics like the overhang moment, for example, and then they sometimes decide to proceed with a single seal design rather than a tandem seal design.
Great, thank you so much. So what other typical components may we have not discussed in high level detail here for the seal gas conditioning system? Anything else we haven't really alluded to?
No, I can take this as well. So the system itself is using either the seal gas from process gas from the discharge side or an external source. So what we really recommend is a filter, a double filter, which allows an uninterrupted flow in towards the seal. Then you have these typical elements like a pressure control valve. Often we have different styles, or most of the time we have different ways of flow control, means a very variable area flow meter or an orifice to set up the flow. So we will provide to our customers the seal leakage, but as well in interaction with the OEM, the compressor OEM, we know the leakage towards the process, so we can set up a flow level which we expect in front of the seal. This can be set up then with flow meters, and especially, or not especially, as well, if necessary, we can provide a heater. The filter elements can be different, so we can, if we have or need to expect a vapor, then we can use coalescer filters, which removes the vapor from the gas. So also the style and the components of the dry gas seal system compared to a standard, in brackets standard, dry gas seal system are the same. Components are the same like normal ones.
Great, thank you so much. A lot of components, a lot of complexities here. So it's really great to see how they're narrowed down and hear your insight and your recommendations. Our next question, earlier we discussed heating up, right? But let's talk about the potential to cool down the gas. So I kind of have another loaded question here, but number one, what is the maximum operating temperature? And then number two, is there any conditioning equipment available via John Crane to help cool down gas?
So there is the designers or our sealers are robust enough to maybe ensure to go up to 200 degrees C. Although we wouldn't recommend it, that's where we would potentially draw the line in terms of what we can achieve and reliably ensure that our customer is satisfied. Then if we go beyond that, this is maybe an activity for development within John Crane, which in some way or form we are addressing, given new applications like Allen power cycle, where temperatures are very, very high. But up to now, now, from my perspective and my experience, we haven't seen many applications with extreme high pressures, except for these new power cycle applications. So, and then from what John Crane can do as a cooling perspective, I'm not quite sure. Maybe Volker, if you're aware more of the product line, you can share with us maybe attempts that John Crane are having to counteract this issue.
Let me check out, because I'm really unsure. I'm not come across with cooling of gas until now, only with heating. But I would like to wade in or to give another insight about these seal temperature. Agreed. We are talking about the seal gas temperature, but we always have to consider the heat generation in the seal. But
Sure.
at the end of the day,
Correct.
the design temperature of the seal will be always a little bit higher than the seal gas temperature in front of the seal, because we have to respect the heat generation within the seal. And we have a little bit of safety margin and say this is about 30 to 40 kelvins difference.
Thank you.
Okay.
Before we wrap up with today's discussion, I want to close out with one more good question here. What are the concerns around corrosion? I know we haven't talked too much about it, but are there concerns for corrosion, and have you seen them arise? And if so, how are you mitigating them?
From a material perspective, we would always deploy the right and the correct suitable materials, particularly from NACE. So all our materials would be some version of stainless steel alloy, which would basically account for an element of corrosion within, I guess, impurities within the process gas. So that, from my perspective, would be under control. There's nothing novel about that, to be honest.
Okay, great. Thank you so much. Gentlemen, this has been a really great discussion. I know we still have quite a few questions on the board that I'm hoping you'll take some time and review and respond to offline. I want to thank you both for your presentation today. I'd also like to thank you for your insight. And I'd like to thank our audience for participating in today's presentation. Again, a lot of really great questions, a lot of interest in this topic. It was really great to see the participation level so high. And I'd also, of course, like to thank John Crane for making today's webcast possible. As we are getting ready to conclude, I'd like to ask our audience if they wouldn't mind participating in a brief survey that'll populate on the screen just after today's presentation has concluded. We greatly appreciate your insight to that. You'll also be receiving an email alerting you when this webcast is available for replay. And we invite you to forward that announcement on to all of your colleagues who may have missed today's live event. That again, thank you to everyone for joining. Thank you, John Crane, and thank you, gentlemen, for your presentations. We'll see you next time.
Thank you as well.
Thank you.
Pleasure.
Thanks all for attending. Thanks. Bye-bye.